Hello, can you hear me? Yes, awesome. Let's see here. Show of hands. First time at the Gordon Research Conference. Hands down, yay. I remember being here, maybe 10, 15 years ago and just enjoying the interaction between the scientists. So it's exciting. Show of hands. Never taking a seismology class before. Okay. Show of hands. I have taken a seismology class, but I do not know all these wiggles and receiver functions. Okay, good. Well, it's exciting to be here to talk about the strength of the outer planet and the paradox related to that strength, right? So, why, if we live on a stable planet that has been resilient for billions of years, should we see weaknesses internal to the outer layer? So that's essentially the puzzle that I'm going to explore today. And we're going to try to use seismology to answer that question. So that's the essential goal of my talk. What can seismology tell us about the strength and weakness in the rocks that make our outer planet? And what new observations can shed light on that? So the talk is in three parts. I'll provide some historical context. Kate has done a great job, but for completeness, I'll do that again. Surprising weakness, observing oldest rocks. And I'll go into the second part, which will be a lot of seismology. Stay with me. I'll try to make it as accessible as possible. We'll look at imaging with scattered waves, why that's a challenge. And we'll look at the new lens that my group is developing to help us see deeper, more clearly into our planet. The idea is building advanced denoising filters that help us build better images. And then finally, very quickly, I'll show new results that might illuminate some of the concerns about the strength internal to old continents. But I'll let us ask questions of myself and one another as we debate which mechanisms best fit the observations. Okay, let's begin. On your screen, you see this handsome gentleman, Joseph Barrel, one of the earliest 20th century thinkers who fundamentally challenged the idea that the Earth's outer shell was uniformly strong. So at the time, they were confronting a curious anomaly. Why was the gravitational pull close to the highest mountains in India, in the Himalaya, weaker than expected? We all know why now, right? We know why now. We've had great talks by geodesists telling us about the long-term response. Essentially, Barrel at the time refined the principle of isostasy and developed the concept that has now endured for over a century. We are not just sitting on a rigid, strong outer shell, but underneath that outer shell is a weaker, ductile asthenosphere. The word asthenosphere showed up in that seminal paper. And as you can see in the figure 14 from that paper. So the concept has become foundational to plate tectonics. We know, or we often attribute the lithosphere to the rigid plates. And we understand the asthenosphere to accommodate over a long time that large-scale movement. And we've refined the idea ever since. But at the time, the idea was related to the mechanical strength, 100 kilometers thick from models, and the motion underneath in the asthenosphere accommodated unloading of glaciers and loading by mountains. So that's the fundamental idea that was handed to us early on. And as Kate has pointed out, this jives with the thermal boundary layer. So you're looking at the oceanic plate. You're seeing a classic plot of depth as a function of square root age, right? The ocean is formed, warm, cold, sits high, and as it thickens, it cools, becomes dense, and sinks into the weaker asthenosphere below. Textbook thermal boundary layer to first order, right? As oceanic plates move away from the mid-ocean ridges, they cool, they become denser, and consequently, they sink. This subsidence is predictably accommodated by the displacement of light water above, and that's how you maintain isostatic balance. So good idea to first order. I know there are more complications, as Kata said, but let's keep to the simple view. Seismic observations in the oceans, as Kate has very well told us, in general, long wavelength view overwhelmingly backs up this idea. On the left, you see that simple half-speed schooling model again. And if you compare the left to the right, you see that the general pattern is consistent. Seismic velocities look like the thermal model. And this is recent global velocity models. And the agreement is striking. If you look at the top of the planet, in the oceans, the lithosphere appears cold, seismically fast, and that is what lends it its rigidity. The underlying asthenosphere below is hot, seismically slow, and weak. So to first order, crucially, temperature directly governs this transition between those two layers. This is the strength of the thermal boundary layer model. The oceans seem to follow that theory beautifully, presenting a clear and consistent picture. But then if you turn to continents, and we try to impose that same thermal boundary layer idea, a paradox, a puzzle immediately becomes clear. And this is what Tom Jordan is illustrating here in his famous continental tectosphere hypothesis. On the left, you see the diagram of rock densities. A block of rock underneath the continents. B, another block of rock at the same depth, but underneath oceans. If you weigh those blocks of rocks, you notice that the rocks on the continents are lighter, and that's important because if the continents are old, they will have cooled more, become dense, and shall sink to such a depth that will have sediments covering the most stable continents, a lot of sediments, or even oceans washing over the continents. That's not what we see. And so Jordan proposed this idea that the continental lithosphere, the continental plate, the continental outer layer, is not just a thermal boundary layer. It is also compositionally distinct. And it's because of this buoyancy that comes from a residue of past melting events that you have lighter, more refractory materials that chemically compensate for that additional thermal contraction, so that when you take those two blocks of rocks down into the mantle at the same depth, they are in isostatic balance. No flow laterally, and you get the continents floating stably. And so that hypothesis is here in action. So we can say that the cryptonic lithosphere can both be strong, cold, but then can last over geological time. We have melt-depleted peridotite. It is inherently buoyant. It is low density, and that affects the thermal contraction. This concept is, as you can see here, is subtle yet powerful. The behavior of the rocks lend a rheological armor, plating the continents, giving them their remarkable longevity over geological time. Okay. And that view from long wavelength tomography and petrology seems to be consistent. If you look at the, on the left, you see pressure temperature relationship from xenoliths, deep mantle rocks brought to the surface by kimberlite eruptions. And you see that the geotherm there intersects the mantle adiabat consistently at around 200 kilometers. Let's see here if I can use my laser pointer. Can you see that? Good, thank you. So that's from the thermal boundary layer idea and the chemical boundary layer idea, where how thick the cratons will be. That seems to be consistent also with a global synthesis of tomography models here. And if you just glance back and forth, up and down here, you see the interior of continents again being cold, stable, thick, essentially homogeneous from long wavelength tomography. And then the puzzle emerges. More observations, especially from short wavelength seismic observations, kind of upend that idea. That's the, I think, most famous paper related to that. What you're looking at is an observation called receiver function, the specific type of observation where the earthquake is coming into the receiver from some place, and it converts to another type of wave at a sharp boundary. And surprisingly, what you see when we collect this observation is that you see another boundary internal to continental lithosphere. It's been referred to as mid-lithosphere discontinuity, and it seems to be robustly observed on different continents, different old continental interiors. So this challenges our view, right? Why do you have this pervasive discontinuity? What processes might cause that? Kate so comprehensively showed us, partial melt maybe, metasomatic alteration maybe, other mechanisms maybe, but whatever mechanism we propose must be consistent with what we think we know, or at least must not present a strong, compelling paradox. So that's the background. But every observation typically comes with challenges, and before we try to test mechanisms, I would argue we should probably do a better job of improving observations. What people often probably know is that receiver function observations are not the sexiest or cleanest observations. They're hard to interpret. And this is illustrated in here. So there are two challenges with using scattered wave to image discontinuities and layering. Challenge one is here. This is S to P receiver functions, so waves that come in shear waves convert to P waves. You get a ping from that layer. The process when compiling an observation is called a deconvolution. And if you look on the left panel, is that observation if you do not do deconvolution. Here in the middle is the same observation if you do a deconvolution. And here are artifacts that are associated with that deconvolution. What you can see, if you look closely at the receiver functions on left, the bottom panel here, is that sometimes, depending on how you process, discontinuities go in and out of focus. That's not good. We would like to know if there are truly discontinuities in our planet. And we also want to be sure about processing artifacts as well. So I'll argue, some seismologists argue that careful data selection, optimized processing can mitigate this. But there's this fundamental challenge. Can we improve the robustness of our observations? That's challenge one, processing artifacts. Challenge two is resolution, and in this particular case, reverberation. So these are, on the left, two ways you might image a boundary. The top is using reflections of S waves, right, as they come in and they reflect before they come into the receiver. The receiver functions are wave conversions. I've talked about them, S converting to P, but also P converting to S. Oftentimes, we will use S waves. This is what an S wave reflection time series looks like. This is what an S wave receiver function looks like. I would argue that if you want to improve resolution, we want to go to P to S because P waves have higher frequencies. But if you compare the P to S receiver functions with its counterparts, even though it has higher resolution, it suffers from reverberations. So those vertical lines will be what you're trying to infer as boundaries, but there seems to be more boundaries in P receiver functions than in S. That's the reverberation problem. And so we want to fix that problem. Okay, where do the reverberations come from? They come from the crust. You're trying to image a mantle layer, a mantle discontinuity, but as the wave propagates upward to the receiver, it echoes multiple times in the crust, and that echo interferes with the signal you are interested in. And so our goal is to remove those offending echoes and improve the images of mantle discontinuities. As you see here, that first and second echo, which are the strongest, arrive at the same time as discontinuities, which are shown as the symbols. And if the crust is thin, about 25 to 30 kilometers thick, that echo is even more prominent interfering with mantle conversions. So how can we improve our results? I'm showing here, just to wrap up this section, a slide of what an observation of P to S receiver function looks like from across North America with those echoes embedded in them. I want you guys to keep at the back of your mind this slide, because the goal, I would argue, is that we can improve this image. You see a single receiver function trace compiled at one seismic station from many earthquakes. You're trying to interpret each arrival as a distinct boundary, but that is overwhelmed by echoes that have multiply reflected within the crust. And so when you look at all the stations, this on the vertical axis, on the horizontal axis here, are just individual receiver functions from all the stations in this map here. It is difficult to say which is a discontinuity from the mantle and which is an echo. That's the challenge. Any question about that? No. Okay, so let's move on. If you have questions, I'll take it at the end of the talk. Okay, so what have we done? We have developed a new method, CRISP-RF, stands for Clean Receiver Function Images with Sparse Radon Filters. At the heart of this method is intelligent denoising that dramatically sharpens seismic images, allowing us to see deeper than before. This is not entirely a new idea. Those words, radon, sparse, they come to us from mathematicians back in the day, two towering mathematicians, Johann Radon on the left. I think he's a Viennese or something like that. I'm not sure. And then Joseph Fourier. But in our application, two-receiver function is novel in the sense of how we use it to denoise, to remove echoes. So I will focus on the key concepts of how we use radon transforms and frequency filtering. I'll gloss over the mathematical details. I'll aim for you to grasp, have an intuition about how this works. And then if you want to discuss, anybody wants to discuss a deeper dive into the theory and the technique, you can talk to me later or just shoot me an email. Okay, let's unpack what's happening. As the name suggests, the core idea is the radon transform. That's an integral transform. It is used for reconstructing images from a set of projections. So if you think about things like CT scans, magnetic resonance imaging, you shove your head into some machine, and that machine rotates around you, takes slices, projections through your head, and that's what's shown here. These are the projections through this image, and the idea is you can reconstruct this image that's rotating from that projection. That's the fundamental idea. In our application of the transform, we are essentially taking this receiver function observation, slowness versus time, slowness inverse velocity versus time, that's the image. And we are essentially rotating that image and taking projections through them in such a way that projections that align with wavefronts that seem to be coming from inside the planet will project it to a different part of the radon space compared to those that are seeming to come from the top of the planet because they have reflected at the free surface. So the behavior of those projections separates them in the radon space. Okay, so this is a toy example illustrating that powerful separation idea. On the right, you see a conceptual radon model. This is what I've been calling the radon space. And on the left, you see the receiver functions that are actually generated from this just by I guess, if you look at that, just by forward projection. So going from right to left is a forward projection. Going from left to right is a back projection. Back projection, we know the idea in seismology. The idea here, though, is slightly different in that we are projecting along something called a curvature, the second derivative of the arrival time of the wave. Long and short, direct waves will be in the top half of that radon space, radon model, and echoes, reverberations will be in the bottom half. And the unique separation allows us then to surgically separate one from the other. Here at around 11 seconds on the top half is a mantle discontinuity. You see it is overwhelmed by the echoes in the crust in the actual data space here. But when you look at it in the radon space, it is clearly separated. So that's the fundamental idea. Let's move on to seeing crisp RF in action applied to real seismic data. Two young gentlemen there who have been instrumental to doing this, both in North America, students of mine, and in North America and in Africa. Jean-Joël Legret, who has a poster about that as well. So what are you looking at? You see a crisp RF in action. You see a receiver function before passing it through the crisp RF filter. It is hard to interpret. It's got considerable ambiguity, noise, arrivals in deeper time. It is really hard to tell which is which in terms of whether it's a conversion or a reverberation. And so then we proceed in three steps. Step one, you take that data on the top, you transform it into the radon model. And now in the radon space, the disentangling is clear. You see in the top region, direct conversions identified as open circles. And the problematic, offending, disgusting reverberations show up in the bottom half, indicated by squares there. Now, we then apply a filter. That's that diagonal line with a little width to it. You suppress everything. You gate everything out that you don't like. Now you have a filtered radon model. The filter is K. You filtered it MK. And then you apply the third step. You just do an inverse projection from the forward projection from the radon model to the actual data. Now you have on the bottom a precisely filtered model in the time slowness space, a beautifully denoised receiver function, dramatically clear, interpretable, and each of those arrivals there are mantle conversions. That image I said to burn in your mind. That's the image on the left. After passing it through the crisp RF, that's the image on the right. The visual difference is striking. So notice how effectively the echoes are suppressed and how prominent, coherent, true mantle arrivals now stand out across the entire stack. And because we are leveraging P waves, compressional waves, you have signals that are at high frequency, typically about 1 hertz, which means that you're really truly getting a crisp, sharp image of the boundaries. Arguably, unlike S2P receiver functions, which are long wavelength and might suffer deconvolution artifacts, the coherence here lends us to argue that this does not suffer the same artifacts. So ultimate takeaway is we have incredibly beautiful images of the continents. We can now reassess if the paradox that was presented to us in the early images in 2010 still remain. The answer is it does. But before we go ahead, let's just again kind of go over what the mechanisms are and how the new observations we're presenting might clarify some of these mechanisms. Okay. At the top, you see one category. I guess this is volatile melting. The idea suggests that fluids or melts, perhaps derived from ancient subducted slabs or even deep mantle plumes that might have some hydration, could percolate, pond at specific depths within the lithosphere, creating this pervasive discontinuity internal to the lithosphere that we see. So a layer that is weak seismically. Other ideas are shown there in the bottom. They might not have come from the past. They might come from maybe more recent present. Say shear-induced fabric from lattice preferred orientation of minerals, or say a hydration, hydrous minerals. I'm not an expert on hydrous minerals. Maybe you can, some petrologists amongst us can discuss the details of that. And one idea that I and co-authors proposed a few years ago, which is a grain boundary sliding process. So this is a subsolidus process in general, where the rock can be weak at seismic frequencies as the waves propagate through them. Now, a key distinction here, I'd say and argue, if grain boundary sliding is a probable idea based on experiments, recent experiments, is that you do not require widespread pervasive hydration or melting. And this might be crucial if you want to reconcile the observation, this new seismic observation, with what we think we know about the evolution of the continental plate. Seems to be potentially consistent with dry, cold, isopycnic continental lithosphere, continental tectosphere model. But I know that we can debate the plausibility of this considering new experiments. Okay, so what does our observation now look like? This is a global compilation of the highest resolution seismic data available, particularly processed through the CRISP-RF method. The map here shows both the extensive distribution of station. Each dot is an estimate of converter depth across the suite of stations we have there. And in the background is an aggregated tomography model. The dark colors tell you when all the tomographic models agree that shear velocities are faster than 4%. And the pattern of the velocities potentially tell us where the cratons are most stable, in addition to other arguments. And then the dots, the color of the dots tell you the depth of that converter. So essentially, the colors in the open symbols, I guess those circles, come from each individual vertical transect of the image here. This is the residual function aggregated for all the stations globally before CRISP-RF, and this is the same residual functions after denoising. What you see visually, but also statistically, we've done the analysis, is that a lot of those converters are at around 100 kilometers, and they are a change in velocity from high velocity to low velocity at around 100 kilometers. And that's why this tomographic model is actually a slice at around 100 kilometers. Discontinuities everywhere, unstable continents, on tectonically active regions. That's the picture. The power of this global approach is that as we improve and compile a wealth of data, then it provides us opportunity to actually not just propose ideas for one region or the other. We want to propose mechanisms that generalize. They generalize to Africa, North America, Australia, South America, Eurasia, generalize to stable continents, ancient cratons, tectonically deformed regions. That's the challenge. Okay. So this is our first attempt. So in the next, I guess, maybe 3 or 4 slides, I'll wrap up now, is our attempt at trying to do that, trying to provide a synthesis, explore mechanisms that might explain these observations. But I'll also appreciate conversations and discussions from the audience and questions as well. So what you're looking at here is that same global compilation, but then organized by what we think the temperature should be at that depth. We've separated that into 2 populations. We've taken a global temperature model constrained from long wavelength tomography interpreted with other observables, geophysical observables, geochemical observables, things like the Cambridge thermal model or the Dublin thermal model, Winter CG, counterintuitive for those who know. But if you believe the thermal model, and you think we know the general composition of continents so that we can then draw a solidus, then at that depth where we have imaged a converter, we can ask how hot is it, and is it hot enough to cause melting today? I know there are other ways to cause melting, we can go into that argument, but I'm just looking at a snapshot today of what the thermal structure is. And so when you are melt, you are hot enough to overshoot the dry peridotite solids. And when you are green, significantly further away. You're so cold, so dry, so depleted that it's really hard to cause melting today. Now, obviously, like I argued, like I said, and Kate has said, there are other ways you might conceive of creating partial melt that might pond at that layer, but that mechanism must be widely applicable to all these particular regions. So the rocks in the red population are significantly hot enough that even with dry peridotite compositions, you can have some degree of partial melt present. They might be present in small quantities, as argued for by DeBile and co-authors in their imaging using both long wavelength velocity and long wavelength seismic attenuation. And they, in their paper, argued that if you take these data together, so the velocity at around 150 kilometers and attenuation at around 150 kilometers, you might have melting small amounts of partial melt. That might, and then I have overlaid on this, where you might have partial melt, those red populations. So potentially, maybe the correspondence of the locations and the depth might be consistent with small amounts of partial melt. Again, I know partial melt models also have their difficulties. How do you retain partial melt at 150 kilometers long enough? If there's high pressures, compaction, but again, no mechanism gives you a free lunch. But I just arguing that this population potentially could be consistent with that view. Okay, so that's the red population. So the green population, stations there that, again, like I said, are cold, cold enough even for wet solidi, what we think if you have some volatiles in the rocks, that it cannot even support partial melting at this depth. So another process needs to be invoked to explain the seismic weakness, to explain the seismic discontinuity. And here at the time is an idea that we proposed, grain boundary sliding, seemed and still seems incredibly compelling. You have a polycrystalline mantle rock. It is subjected to stresses, and it can deform internally elastically within the grains, but also there can be sliding. There can be a deformation along the grain boundaries. At very low temperatures, grain boundary sliding is limited. Deformation is elastic. If you bring the rock, the aggregate rock, to some high temperature, but not too melting, you can weaken the grain boundaries. And then as you deform the rocks at seismic frequencies, the rock will appear to be weak due to that sliding along the grain boundaries. The critical insight here, what you're seeing in this map, is the individual stations at that depth and the characteristic frequency at which the grain boundary sliding is expected to occur, if you believe experiments from 10 years ago. The depth in general seems to agree. The depth at which the sliding should occur seems to agree with some of the depths from where our scatterers are. So essentially, we're taking all those scatterers and asking, where is the temperature, preferred temperature, and does that temperature cause the characteristic frequency of, or overlap with the characteristic frequency of sliding? Okay, I did this talk before I heard the talk from, I think, Tom. And so there, I know this mechanism is still an active area of research and debate. You know, if you prepare the experiments differently, you might see different things. There might be weaker modulus relaxation and things like that. But we think, at least from the arguments we are making here, that this seems to be compelling. So the depth and temperature ranges where the relaxation is predicted to occur by mineral physics experiments at the time perfectly coincide, or generally coincide, with where we observe our scatterers to be happening as we map them onto published thermal models. We can discuss more about what this what other mechanisms might explain, but I just wanted to leave it there and pause and just thank all the members of my lab that worked on this, in particular, the PhD students, and to point you all to Jean-Joël Legre's poster on the observation that we've compiled, in particular in Africa, and how we've explained this discontinuity from these new observations. Thank you. I'll take questions now.
Great. Thanks for that wonderful talk. As usual, we'd like to start with questions from an earlier career researcher like Sean.
Thanks for the talk and the introduction of your strategy of the platform, the most percentage in the common environment. I think my question is about the rate of transform. My understanding is that there are many other factors can also produce positive and negative based on receiver function. For example, DP, isotropy, disalinity, and SLP. And this effect can be easily observed when sorting receiver function by azimuth. So I think my question is quite simple. It's just whether radial transform can handle can do the good job in a complex structure that with or with basic zone SLP.
Gotcha. Spectacular question. Question is, receiver functions are more complicated than I have argued they are. That they don't just vary with slowness, they vary with back azimuth, and there are other reasons why that can cause those, right? That's the question. And can radon transform handle that? The simple answer is yes, radon transforms can handle that. At the moment, we are assuming that the receiver functions are primarily just recording isotropic velocity changes. So that's the way we've conceived of the radon transforms now. Now that might be underwhelming, right? Because there are many observations that suggest that there's anisotropy in the crust and the mantle. The images I've shown do not account for that. However, when you see a strong arrival in the radon transform, it is because that arrival obeys or conforms to that assumption. So what I'd argue is that every image you see there in that converter suggests that this is just an isotropic velocity reduction. Now, is there an isotropy? Yes, but the technique at the moment will not recover that. Is that satisfactory? Yeah, so if you wanted to do a radon transform for anisotropy, you'd have to code that up into the equations so that then you can back project correctly. You can back project not just along slowness, you can back project along azimuth as well as slowness.
Andrew Berkey, Michigan State. So one of the really interesting observations that STP receiver functions made recently is that there are regions like Australia, the African cratons, and North America where you see multiple MLP phases. Do you still observe those, or are you removed with the radon transform?
Good question. Simple answer is yes. We do observe places where you have not just a velocity reduction, you have both a velocity reduction and a velocity increase. This is good work by the Brown group and yourself probably as well, that suggests that the discontinuous structure can be complicated within cratons, but also outside of cratons. And that's what you're seeing with those extra blue phases, right? Inside maybe from 400, stations organized from 400 to 600. But if you're just to say, okay, I don't know where the converters are coming from, I don't care for the stations, just put everything in one giant big matrix, which is what that is, you see that the most coherent arrival is that velocity reduction. That's all I'm arguing. I'm saying on average, what's the strongest conversion and what's the most prevalent conversion is velocity reduction. But sometimes you see arrivals deeper. Those deeper arrivals are not coherent globally. And potentially that's why when you do a global stack, you don't see a strong converter. In Africa, when we looked closely in Africa to do a detailed check, we noticed that those extra arrivals typically happen when you are in the lithosphere that's been rifted, broken, or a lithosphere that is being compressed at convergent boundary, or the lithosphere that has potentially gone through multiple episodes of assembly and reassembly. It is only in Africa that we've done that kind of detailed work. So I don't know if that answers your questions.
Here,
Yeah.
hello, Emmanuel, Carnegie Science.
Yeah.
Thank you very much. I learned a lot. I'm a petrologist.
Awesome, seismology.
So my question is about the last part where you were evaluating the main hypothesis about what's causing mid-lithosphere discontinuity. So it seems like you're more into supporting the green boundary sliding. And is that consistent in terms of when you look at conductivity constraints, where I would imagine that the partial melt would be more sensitive to partial melt, like conductivity?
Yeah, spectacular question. It might look like I am in favor of elastically accommodating green boundary sliding. I'll say probably that's not the way to think of it. It's maybe my lack of creativity at the moment with all my understanding of other mechanisms. But the question is well taken. What other geophysical observable can you place alongside seismic observable that might disentangle one mechanism or the other, either strengthening partial melt, for example, or potentially rule it out at the same locations where I have image converters? That is perfect. I am not a magnetotelluric expert. I think Samer might be around here somewhere. Where's that, Samer? He's sleeping. Oh, no, he's right there. So opportunities then to expand the observations and ask that question. Samir, what are your thoughts on that? Maybe discuss it later.
I will just say that there's the US array.
There we go. So the magnetotelluric experts are sitting together.
So I think the comparisons just need to be made.
Yes, exactly. Yeah. There we go. There we go.
Poster number 12.
Good. You're welcome. Am I the one choosing who to speak? I trust yeah, go ahead.
So I'm Emily Chin,
Yeah.
Scripps. Thank you for that. It's really interesting. I work on Cratons
Yeah.
on Thursday. But can you go back to your map where you showed no melt areas that you correlate with EA GPS? I'm just curious because these sort of correspond. You had another map that looked like they were more on the Proterozoic areas of the continent.
This one?
Yes.
Mm-hmm.
And can you comment on, do you think there's a difference why you see that there? In some of the Archean cores, you don't see this process. So does that suggest the Archean cores are...
Can you be specific? Just give me a specific example.
So your gray, your tan areas, right? Are,
Yeah.
Are older.
Yeah.
And those don't have your EAG.
Yeah. So good question. So what you're looking at here is a global map. So forget the symbols for a bit. Is a global map of translating temperature to the characteristic frequency of grain boundary sliding. Wait for me. And then the symbols are where I have stations. So when you don't see an overlap, doesn't mean that there might not be that process occurring. It might just be that I don't have stations there, or and that there is the overlap. So for example, in North America, you see good correspondence, especially in the cores, but also extending out from the cores out to more younger areas. But there are uncertainties associated with the translation of temperature to grain boundary sliding depth, in such a sense that when I say near, at, or above, this is considering uncertainty. So for example, a region that might be brown, that might be blue, might actually be brown if you account for uncertainties. Does that make sense, how to read that image? Yeah, good.
Thank you for talking of your bold color schemes. Do you mind going back to the LODD you had a couple seconds ago?
This one?
Yeah, this one, yeah. So I noticed that, especially in North America, it's quite sort of salt and pepper. Right? It's on small.
Gotcha. Yeah. Small lens scales. Yes. Yes.
In Africa, it's more consistent, but I guess
Yes,
I'm
yes.
wondering, is there anything in the results that we to do with
Yeah.
the amplitude or
Yeah.
something about how these discontinuities look that matches at a slightly smaller scale than just kind of the binary, like it's
One or the
Western
other.
North America, it's Eastern North America, it's cold, it's hot. Is there any more nuance that
Yes, there is.
aligns with other maps that we have?
There is. Yeah, there is. So, for example, your the work that you and the Brown Group have been doing, we've done a thorough study to see, okay, what are the controls like in Basin and Range, in along Yellowstone? How does some of that tectonics inform where the depths will be? And there's more nuance, and we did that discussion in those papers. And there's also complexity, right? There's complexity, like the early career scientist pointed out with anisotropy, how would that look in the final image? But regardless of that, you're saying there's salt and pepper, right? Yeah. I'd say it's mostly salt, little pepper. That there's a consistency. There's a consistency in the depth, on average. Does that make sense?
Yeah, they are all clearly in a similar range, which is
Exactly.
what we and other people have seen. So
Yeah.
I was just wondering if with this enhanced method, there's anything where geographically they collapse a little bit more, so
Yeah.
they're sort of a little bit more mutually consistent. And then
I see. We can do that analysis as we look globally as well. So we can. What I hear you say, or the question I ask is, can we measure how correlated spatially and depth-wise this discontinues, especially where you have very good coverage, say for North America. So 2 stations in the same tectonic province, how different is the depth? And when they are not different, can I give you a map that says where, and potentially maybe help disentangle why, right? I haven't done that analysis. My intuition is they are more consistent than this map will suggest, because we've looked at them over and over again. So the funny thing about putting symbols on a projection is they distort true coherence. So when you're looking at the map, there's a lot of distortion. If I was to zoom in to North America, that kind of weird salt and pepper thing will go away. Trust me on that.
So it's almost eerie, Zach. I was looking at exactly the same thing. But let me ask the question a little bit differently. I'm really intrigued by the somewhat deeper and more uniform depths you're getting in the African cratons, particularly in southern Africa, where we've got the better sampling, relative to North America, which does indeed look very, I mean, I agree with
heterogeneous,
similar
yeah.
depth range, but it's shallower, as well as being somewhat more heterogeneous. So have you thought at all about what might explain that difference?
I see.
And how that might shed light on a mechanism where the MLD is produced by sort of collection of metasomatic products versus the elastically accommodated grain boundary sliding?
Fair question. The simple answer is I hear what you're saying, and I'll say maybe not. So we should do a more thorough job of making those comparisons. So I'll say maybe not. We've not done a thorough job of looking at those comparisons and say, okay, why is it consistent in Southern Africa, more consistent spatially in Southern Africa than, say, for example, in North America? But those are good points that we will explore. Thank you.
Hi, Colleen Dalton.
Glenn.
Brown University. Thanks for the nice talk. You described the RF method as a way of separating the main arrivals from the echoes and effectively cleaning up your receiver functions. Can you do anything with the information in the echoes?
Oh, you bet. We wrote a whole paper about echoes. Thank you for that question. I'm so excited. Yeah, so so while the echoes might be of little interest if somebody wants to see the mantle, right? They are of spectacular interest to a person who wants to know what the crustal structure is. And so we wrote a whole paper about how the sharpening of those echoes and knowing the detailed curvature of those echoes can be put into inversion to improve things like H-kappa stacks. We did that for P2S receiver function, but we can totally put that into another echo for S2P receiver functions. Now, S2P receiver echoes arrive after the main arrivals, but then you can shove now that S2P echo into an inversion that will brighten images of the moho. So simple answer is, echoes are not all bad. They are useful, and yes, we have done that. Thanks, Colleen.
Great. Maybe one last question from Karen.
The melt map is really surprising to me. So the entire western U.S. is molten at 50 kilometers depth above the dry solids. So that must be an extreme mantle potential temperature everywhere. Or there's CO2 or something. But I don't think we think that the mantle is above its dry solids at 150 kilometers.
I echo your concern, and I say yes, I agree. So I will probably punt to someone else to take that question. But what I'm showing is not exactly what we know, meaning we do not know exactly what the temperature is in the western U.S. Let me show that map. So, yeah. So when I say it is okay, let me do this one. Oh yeah. So that's the thermal model. It is a model. It is a model of what temperature should be at these locations on the continent from jointly inverting seismic velocity, shear wave velocity, and other geophysical observables, and potentially also geochemical observables. So that's one. So I'm not going to stand behind this model. This is something I borrowed from a seismologist who think he can build seismic thermometers. That's one. The second thing also is we do not know, or I do not know, the solid dust everywhere in the western US. But we think we know what the solid dust is. And when I do just that simple-minded estimation is, then you can say, okay, these regions are hot enough if you believe the seismic thermometers to be molten. But the question is well taken. What's happening in Western Africa, Western US and other places like that? Can somebody go in and essentially validate the conclusions that I'm making from these models? Does that answer the question without answering the question? Yeah.